Welcome to the first of several videos on vector cross products. The goals of this video are to determine the cross product of two vectors in R3, verify the cross product of two vectors is orthogonal to the given vectors, and then also determine the angle between two vectors. To determine the cross product of two vectors, we can evaluate a 3 by 3 determinant where the first row would be the I, j, k vectors. The second row would consist of the components of vector u, and the third row would be equal to the components of vector v. And there are several ways to evaluate a 3 by 3 determinant, but we'll use the cofactor expansion method, meaning we'll first eliminate row 1 and column 1. The remaining elements here will form the 2 by 2 determinant that we see here. Then we'll multiply that by vector I, and then we'll subtract the determinant formed by eliminating row 1 and column 2. To eliminate row 1 and column 2, notice we'll have u1, u3, v1, v3, which we see here. We'll multiply that by the j vector, and then we'll add the value of the determinant formed by eliminating row 1 and column 3. So we see here u1, u2, v1, v2, and then multiplying that by vector k. Now what's special about the cross product of two vectors is the result is another vector that is orthogonal or perpendicular to both vector u and vector v. Let's take a look at this. Here's an illustration where we have the cross product of the red and blue vector. And what I want you to notice is that the black vector, or the cross product, is perpendicular to the red vector, as we see here, as well as being perpendicular to the blue vector, as we see here. So the black vector is the cross product of u and v. Now you might be wondering, why is it that the cross product, or the black vector, points in this direction rather than the opposite direction? And that's an important thing to consider. And before we take a look at this in more detail, I want you to be careful not to confuse the cross product of two vectors with the dot product of two vectors. Remember, the dot product results in a scalar or numerical value. However, when we cross two vectors, we get another vector that is perpendicular to both. Okay, so let's talk about how we determine what direction the cross product vector will go. This is called the right hand rule. What we're going to do is take our right hand and point our fingers in the direction of vector u, so that when we close our hand or bend our fingers, they bend toward vector v. So for example, in this diagram here, if we point our fingers in the direction of the u vector with our thumb pointing up, if we bend our fingers, they will bend toward vector v. Our thumb points up, so the orthogonal vector will also point up. So the order in which we cross these two vectors is important. We point our fingers first in the direction of u so that they fold or bend toward v. If we switch the orientation of the two vectors, if we want our fingers to close toward vector v, we'd have to have our hand almost upside down so that our thumb points down, so that if we bend our fingers, they would bend toward vector v. The thumb would point down, therefore the orthogonal vector would point down. So this is the right hand rule, and this is how we determine what direction the orthogonal vector will go. Let's take a look at an example now. We want to determine a vector that is orthogonal to both u and v, so we'll have to find the cross product. So we'll have u cross with v is going to be equal to a 3 by 3 determinant where the first row consists of the I, j, and k vectors. The second row consists of the components of vector u, so we have 3, 1, negative 5. Third row consists of the components of vector v. Now we'll go ahead and evaluate this. The first 2 by 2 determinant will consist of the elements remaining after eliminating row 1 and column 1. So we'll have 1, negative 5, negative 2, negative 3. We're going to multiply this by the I vector, and then we're going to subtract the 2 by 2 determinant formed by eliminating row 1 and column 2. So we'll have 3, negative 5, 4, negative 3 times vector j plus, now we're going to eliminate row 1 and column 3, so we'll have 3, 1, 4, negative 2 times vector k. Let's go ahead and evaluate this. We're going to have negative 3 minus positive 10, that's going to be negative 13 times vector I, minus, here we'll have negative 9 minus negative 20, which will become negative 9 plus 20. It'll be positive 11, but we do have this minus sign here, so I'll have minus 11j plus, here we'll have negative 6 minus 4, that's negative 10 times k. So instead of writing plus negative 10, I'll go ahead and just write minus 10k. So this vector should be orthogonal to both vector u and vector v. Let's go and take a look at the graph of this. Now it's a little hard to interpret this because we're looking at a three-dimensional graph on a two-dimensional surface, but you can see that this blue vector here, the cross of u and v, is perpendicular to both the red and brown vectors as we see here. Now that we have found u cross of v, let's verify that this vector is orthogonal to both u and v. Remember, the way we can verify this is if we dot u and the cross product and v and the cross product, if that dot product is equal to 0, those vectors are perpendicular. So we have to calculate two dot product. First we have to dot u with our cross product to make sure this is equal to 0. Then we have to dot v with the cross product. So let's go ahead and verify this. Here we'd have 3 times negative 13, that's negative 39, plus 1 times negative 11, that's negative 11, plus negative 5 times negative 10, that's 50. Well, this is negative 50 plus 50, so that does equal 0. So these two vectors are perpendicular. Let's go ahead and check to make sure the cross product is perpendicular with vector v. Here we'd have 4 times negative 13, that's negative 52, plus negative 2 times negative 11, that's 22, plus negative 3 times negative 10 is 30, and again this is equal to 0, so we have verified that the cross product is orthogonal to both u and v. And before we move on, let's go ahead and talk about some additional properties of cross products. The magnitude of u crossed with v is equal to the magnitude of u times the magnitude of v times sine theta, where sine theta is the angle between the two vectors. Number 2, u crossed with v equals 0 if and only if the two vectors are scalar multiples of each other. And then lastly, the magnitude of the cross product equals the area of the parallelogram having u and v as adjacent sides. Now we'll talk more about these in future videos, but let's go ahead and take a look at one example of this first property. Going back to the same problem, we can use this property to determine the angle between our given vectors u and v. Let's go ahead and try to do that. If we solve this for sine theta, we'd have sine theta must equal the magnitude of u cross with v divided by the magnitude of u times the magnitude of v. Once we find this, we can determine the angle between the two vectors. Let's give it a try. So here's u cross with v. We need to find the magnitude of this. We have the square root of negative 13 squared plus negative 11 squared plus negative 10 squared. Our denominator is going to consist of two different square roots. First, the magnitude of u, the square root of 3 squared plus 1 squared plus negative 5 squared. Multiply this by the magnitude of v, so we'll have 4 squared plus negative 2 squared plus negative 3 squared. Now to save a little bit of time, I've already simplified this. This comes out to approximately 19.7484 divided by approximately 31.8591. Now using some trig, if sine theta is equal to this ratio, that means arcsine of this ratio would give us angle theta. So let's go ahead and get our calculators out and give that a try. Let's first put our calculator in degree mode. Notice I'm already in degree mode here. So now we're going to press second sine for arcsine or inverse sine. Then we'll just type in our ratio. So the angle between those two vectors is approximately 38.3 degrees. Okay, that's going to do it for this first video. Thank you for watching.